So you want to get into robotics, but you don't know where to start. Here are 5 robot builds you can actually finish this summer, ranked from easiest to hardest. So pick the one that matches where you're at. First up, a robot pet you can build for less than $40. No fancy parts, no soldering nightmares, just a fun weekend project to get your feet wet. Next, a DIY robot dog that skips the 3D printer entirely. If you don't own one, or just don't want to deal with one, this build gets you a full quadruped using parts you can source directly. Then things get more technical. An open-source ESP32 companion robot, small enough to sit on your desk, but built entirely from scratch. Code, electronics, and all. Level up again with a full quadruped robot dog, also ESP32 powered, also open source, walking you through the entire build, from bare board to a robot that actually walks. And finally, the hardest and coolest build on this list, a quadruped robot dog so small it fits in the palm of your hand. Miniaturization changes everything, and this build shows you exactly how it's done. 5 robots, 5 skill levels, 1 summer. Let's build.
Hello, thinkers. What if you could bring a new form of life into the world? An artificial creation that walks, moves, and learns with you. In this video, I'll show you how to build your own robotic pet from scratch. It's not just a toy, it's a functional marvel with 8 degrees of freedom and a brain powered by the mighty ESP32. If you're looking for an introduction to using an ESP32 board or servo motors, check out our dedicated video, link in the description. Let's get started with the first step. First, I downloaded the 3D model of the robot's frame and leg components. These parts are 3D printed to ensure they're lightweight, precise, and strong enough to support the robot's movements. Next, I attached the servo motors to the 3D printed legs. These servos will act as the robot's muscles, providing the movement for each joint. It's important to align them properly to ensure smooth operation later. After securing the servos, I connected the legs to the main frame. The result is a sturdy but flexible structure ready to move. Now it's time to connect the servos to the driver board. This is a 16-channel PWM servo driver, which allows us to control multiple servos simultaneously from a single microcontroller. Each servo is connected to a specific channel, and the board communicates with the ESP32 via I2C. This makes it easy to control all 8 servos with just 2 data lines. With the servos connected, it's time to complete the assembly. I added spacers to secure the frame and mounted a support for the ESP32 board. I'm also using an ESP32 shield, which organizes the connections for the driver, the distance sensor, and the power supply. This setup keeps everything compact and easy to manage. Now for the exciting part, programming the robot to walk. I started with a simple sequence to make it move forward. The combination of precise servo control and a lightweight design makes this robot surprisingly smooth in its movements. And this is just the beginning. Future updates will make it even smarter. Building a quadruped robot is an incredible experience. Watching it take its first steps is rewarding, and there's so much potential to make it more advanced. And now, by giving it its own power supply, I've made it a completely independent creature. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments. In the next episode, I'll show you how to program more complex movements and maybe even teach this robot some tricks. See you next time.
I wanted to create a small robot dog that could live on my desk. I wanted it to be inexpensive. In fact, you can build your own for less than $50. It can walk, avoid obstacles, play, and just mess around. It took me months to find the right material and a structure that's cheap, strong, and easy to repair, like swapping a servo. I'm sharing it hoping it helps you build your own. For the body, I used simple PVC sheets. They are cheap, lightweight, and very easy to cut and assemble. I started with the legs. Each leg has 2 degrees of freedom, which means 2 servo motors per leg. I cut 2 simple PVC pieces and attached them directly to the servos. The servos are mounted in a way that makes them easy to remove and replace. This is important when experimenting, because servos are often the first components to fail. This part is crucial, so grab a coffee and get comfortable. It's almost time to test the first leg movement. But first, let's see how to use the servo driver. All the servos have to be connected to the servo driver, which communicates with the ESP32 via I2C. This means the 2 wires, SDA and SCL, should be connected to GPIO21 and GPIO22 on the ESP32. Then connect VCC to 3.3 volts and GND to ground. Finally, don't forget to connect the servo power supply to VIN. Now we can upload the code and get the first movement of a leg. And even 2 legs if we connect another servo to the driver. Once the legs are working, I build the main body. This square backplate holds the electronics and connects all 4 legs together. On top of it, I mount the ESP32 and the servo driver. finally added the neck. I cheated a little by using a 3D printed support for the ultrasonic sensor, but you can literally glue it to the servo mount. I connected the neck servo to the last channel of the servo driver. The ultrasonic sensor is directly connected to two GPIO pins of the ESP32. For more details, you can find an introduction to ultrasonic sensors in another video. Link in the description. To make the robot energetically autonomous, I used a power bank. It's not very elegant, but it's cheaper than buying batteries and all the circuitry needed to charge and regulate them. The moving head gives the robot personality. It can look toward nearby objects and react to its surroundings, and even with very simple logic, it already feels much more alive. I also wrote a modular control framework that I'll share, designed to make the robot easy to control and extend. In the next video, I'll dive into the code. The full code will be shared, so you can build on it and make this robot your own. If you appreciated this project, don't forget to like and subscribe. What if your robot dog could fit in your pocket? This is Micro Albert. 4 legs, 4 servos, a tiny OLED screen, and it lives on my desk. It walks, does tricks, tells me the time, the weather, and yes, even my YouTube subscriber count. And every single file, code, 3D models, schematics, is completely open source. I already had Albert, my quadruped robot dog, and I just thought, can I make it smaller? But the moment I started redesigning everything from scratch, it stopped being a shrink job and became something completely different. New chip, new case, new battery solution, new wiring strategy. Micro Albert is its own thing. Here's what's inside. 4 SG90 microservos. These give you the 4 degrees of freedom, 1 per leg. A small OLED display over I2C, and the brain, an ESP32C3. I chose the C3 specifically because it's tiny. Smaller than a classic ESP32, still has Wi-Fi, and most importantly, it fits the case I had in mind. No servo driver this time. On the full Albert, I used a PCA9685, but here I'm driving all 4 servos directly from GPIO pins. Fewer components, less space, simpler routing. Now the battery. This is my favorite part of this build. I started with a cheap power bank, cracked it open, pulled out the internal LiPo cell and the charging circuit. That gives you a clean USB-C rechargeable battery pack without paying for a dedicated solution. But even the stock LiPo was too thick for the case I designed, so I swapped it for a smaller, thinner cell. Same chemistry, just a tighter footprint. The charging board doesn't care, it still works perfectly. I made a small shield that sits right on top of the ESP32C3. Each servo signal wire goes to a dedicated GPIO. I'm using pins 0, 1, 2, and 3. Power and ground are shared from the battery rail. The OLED connects via I2C, SDA, and SCL. 2 wires, that's it. The light post slides into the base, the charging board sits flush at the back. Everything clicks together, no screws on the main body. Everything I just showed you is on GitHub. Link in the description. STL files, firmware, wiring diagram, BOM. Fork it, remix it, make it your own. If you build one, drop a photo in the comments. I genuinely want to see it. And if you want to see how the full-size Albert works, or how I'm training it with reinforcement learning and simulation, that video is right over there. Thanks for watching. This is Albert. He's the 3D printed evolution of my PVC robot dog. And he's officially taken over my desk. Browsing the internet, you'll see commercial robot dogs costing anywhere from hundreds to thousands of dollars. But Albert costs less than $50 to build, and I am completely open sourcing this entire project. I'm sharing the STL files, however, if you don't have a 3D printer yet, go check out my previous video where I show you how to build the chassis out of simple PVC sheets. Everything you see, the STLs, the wiring diagrams, and the modular code, is live on my GitHub page right now. In my previous video, we built the body. Today, we're giving him a brain. I'm breaking down how to create complex behaviors, and I'm going to show you how LLMs like ChatGPT, Claude, and Gemini are changing the way we do robotics forever. And finally, wait till the end for some tips on powering Albert properly. I had a lot of issues making him battery-powered, and I want to share exactly what I learned, so you don't make the same mistakes. To bring Albert to life, the first step is defining what I call gate primitives. Instead of using inverse kinematics, I'm using simple cosine functions. I use a standard cosine for the upper leg to handle the forward swing, and a rectified cosine for the lower leg. By cutting that lower wave so it never goes negative, I can mimic a cycloid pattern. This ensures the foot lifts high enough to clear the ground and then glides forward. To steer, I'm using amplitude modulation. To turn left, the code simply increases the movement amplitude on the right side. Now we can proceed by defining a motion logic. This part I did using Claude, which saved me an incredible amount of time. I simply inserted my primitives into the prompt and asked it to follow some specific logic. For example, look around with the neck, and when you see something closer than 30 centimeters, go in that direction. Similarly, for the autonomous exploration mode, I asked Claude to follow this logic. Go forward, and when you see an obstacle, look right. If it's free, go there. Otherwise, look left. And if both sides are blocked, simply go backward. Now, let's talk power. Originally, I looked into a standard LiPo setup, a high discharge battery, a charging module, and a step-up converter to get a stable 5 volts. But that stuff adds up fast. It was going to double the cost of the robot. So I decided to hack the system. I bought a basic $5 power bank and decided to take it apart. Inside, you find exactly what you need: a high-quality lithium cell and a pre-made circuit that handles charging, protection, and a rock-solid 5-volt output. But even with the power bank, I ran into a major wall. During testing, the legs were incredibly unstable, twitching and causing the ESP32 to reset every time Albert tried to take a step. At first, I thought it was my code, but then I realized the problem was hardware interference. The servos and the ESP32 were sharing the same power line. When the 8 servos kicked in, they created a massive voltage drop and electrical noise that choked the microcontroller. The fix? I leveraged the power bank's dual output design. I ran one dedicated line to the servos and a completely separate one to the ESP32. Instant stability. Albert is a testament to what you can do with a $50 budget, some 3D printed parts, and the help of AI to bridge the math gap. He's my new favorite desk companion, and he's ready for you to build him. If you enjoyed this deep dive into the brain of Albert, hit that subscribe button. Let me know in the comments what behavior I should teach him next. Thanks for watching, and I'll see you in the next one. This is Albert, and this is Albert Mini. This might be the smallest fully self-powered open source robot dog ever built. Same 8 degrees of freedom as the full-sized version, just fits in your hand. But fitting everything into this small design was a challenge. Getting here almost didn't happen because of one part. I didn't have to code and train the robot. Thanks to LLMs, I could just ask for complex tasks in natural language, and he figured out exactly how to execute them. All this project is open source. Code, 3D models, everything. If you like projects like this, sharing it helps a lot. If you've seen something smaller with these specs, let me know in the comments. I'd love to see it. To make this work, I had to redesign the body around a specific goal. I wanted Albert Mini to fit in my hand, but I still wanted to use standard SG90 servos, so they are easy for everyone to buy. But because the upper leg is so small, I had to create a special design where the horns of the two servos actually partially overlap. It took some fine-tuning to make sure they didn't collide, but it allowed me to keep the full 8 DOF motion in a tiny footprint. Inside, I used a servo driver to control the motors and an ESP32, which I fixed right on top of the box that makes the body. For more info on how to connect everything, check out my previous videos on the topic. I'll leave the links in the description. Then came the battery. To make design even smaller, I could have used a tiny LiPo battery, but that would mean low capacity, short run times, and I'd need a dedicated step-up module. Instead, I decided to use a standard power bank. By placing it right on top of the robot, it solved the balance issues and gave me hours of battery life. It's not that bad. It actually looks like a nice hat. One thing I really focused on was making sure the design stayed modular. Everything is easily fixable. Here you can see me replacing a broken servo in less than a couple of minutes. Now, here's how the brain works. I don't command him by hard coding every move. First, I inform the LLM about his physical build, his joints, and his 8 degrees of freedom for locomotion. Once Gemini understood the body, I could just ask for behaviors in plain English. I can tell him to do push-ups, swing, dance, or even jump. I'm basically just the coach. The AI figures out the motor positions to make it happen. Here you can see a few examples, but you can imagine many more. Let me know in the comments. It's not always perfect, but it's changing how I do robotics forever. The smaller these get, the more interesting it becomes. You can build a sophisticated quadruped right on your desk. Next step, making him fully autonomous. What behavior should I ask Gemini to try next? Let me know in the comments. Also, let me know if you are interested in a video comparison between ChatGPT, Gemini, and Claude to see which one is actually better at understanding a robot's body and generating motion. Go grab the files on GitHub to start your own build. I'll see you in the next one.